Hi everyone. So in this video we have a brief discussion of one mechanism to handle the cases where, or the applications where, the input and output have different sequence lengths. And these class of architectures that we'll discuss are called encoder-decoder sequence-to-sequence architectures. And as the name suggests, basically it consists of an encoder, which in that example plotted in the plotted here in the notes, it has hidden-to-hidden recurrence. So you have the input at every time step, go into the hidden layer at every time step, and then the hidden layer of one time step is connected to the hidden layer of the next time step. So basically the encoder can be summarized as X and then go into H, right? And then you have H one time delay, right? And here you have W for the state-to-state transition. And then at the end of, so there is no output in all the encoder steps. And then at the end, you output what's called the context. So you output only one output vector that could have an arbitrary length, right? So it doesn't have to be the same as the length of the input vector X. And then the context is input to the decoder, right? The context can be fed to the decoder as an initial state, right? So as in this case here, or as an input, as in these arrows right here, right? So this is all the context being fed as an input to the decoder, right? And another option is you could even have connections directly from the context into the output, affecting the output sequence Y1, and of course there are weights assigned to learnable parameters, weights over all these arrows. And in this case, right, the decoder has also another connection from the output at one time step to the input in the next time step. And this is basically, this is the most general form that you could have to mimic the fact that the joint probability equal the joint conditional probability of the y's given the x's equal P of y1 given x times P of y2 given y1 and the x's times P of y3 given y1 and y2 given the x's, and so on, right? If there are conditional independence between the y's given the x's, then you could remove these arrows right here, right? So one application where there is a perfect match between this encoder-decoder idea and the nature of the application is basically think of voice assistants or translators, speech translators, where first you convert the input sequence, right? So in the case of voice assistant, you have an input sequence which is a voice signal, and then, or maybe words, individual words, and then you interpret the sequence of words into a representation, and then from this representation there is an output sequence. There is the answer, right? The voice assistant, the automatic voice assistant would do what? You would tell them a sentence, they would hear it, interpret it, and then they output another sentence. The two sentences do not have to be the same length. The translator, same thing. It translates a sentence, right? So it doesn't have to be a speech translator, maybe a natural language processing translator. And so it translates a sentence from one language, it represents it, and then it outputs in another language, right? Ideally, if the input and output, if the encoder and the decoder belong to the same, so think of it, imagine you're building a repertoire of encoders and decoders for the different languages, right? And the sanity check while you're building them is that if I have an encoder and decoder of the same language, I convert to the context and then I reconstruct, I should reconstruct the same sentence, right? Now for the case of languages, one candidate for this context is what's known as universal there is a lot of work in natural language processing that started with the work introduced by Chomsky on universal representations of languages, right? So it's like a universal language, a universal way to represent semantics, right? So this could be an intermediate between the different languages, right? So it happens to be an excellent match for speech recognition and generation and natural language processing in general applications. So that's why actually a lot of advances that happened for these kind of architectures happened as in the first work above, for the application of natural language processing and statistical machine translation. So if you are curious more about these architectures and what are the challenges with their training and how to determine the context, like the format of the context, how to determine the structure of the decoder, whether the context should be provided as an initial state or as an input or no, whether there should be a shortcut between the context and the output sequence or no. You're welcome to check these two papers. One is called Learning Phrase Representations using RNN Encoder-Decoder for statistical machine translation, and the second is called Sequence to Sequence Learning with Neural Networks. Thank you.